This will be really informative for anyone that either has done vibrational analysis with Inventor Nastran or another software, or if you're familiar with simulation using Inventor FEA or Inventor Nastran and you're looking to sort of start to analyze some vibration in your designs, maybe take some of your simulations to the next level with things like frequency response and random response. So I will be going through just sort of some of the background information about these types of analyses and what you can expect and some of the things and some of the factors that come into play with each of these. And then I'll be going through a demonstration showing you the setup for how we run these analyses and what type of results we'll get, how we can interpret those, and how we can kind of approach the next steps of our design process. So first off, if you haven't really been introduced to Nastran already, this is a finite element analysis software. So we're looking at FEA. We're breaking our geometry up into nodes and elements and using those to calculate the displacements and the resulting stresses in the elements in our models. This was originally created by NASA, actually, in the 1960s, well, in conjunction with NASA in the 1960s by MSC. This was eventually acquired by Autodesk, and it stands for NASA Structural Analysis. So it is embedded in Inventor as an add-in. This is nice because if you are familiar with like a tool like Inventor FEA or SolidWorks FEA or any of those other tools out there that are CAD embedded, this allows you to take your 3D model that you're working in Inventor on and immediately apply your finite element analysis without having to export out the shape and work in a different software. So it allows you to make these analysis in Inventor, and then you can still keep your assembly or your part in Inventor, and you can still continue to use tools like Vault for other product data management softwares as well. So once you have Inventor Nastran installed, it actually will just load directly into Inventor. You don't have to open up any other softwares. It will be available as soon as it has been downloaded. It has now been included in the product design and manufacturing collection. So if you have a subscription to that, you will have access to Nastran as well as other really great tools like Inventor HSM for machining. You can get AutoCAD. There's a lot of really great tools out there in that product design and manufacturing collection. So what are some of the things we can do? Some of these are, you're probably already familiar with. We've got the basics, linear static stress. We can apply a load where we're expecting small displacements, and we're really just looking at if everything was static and we apply some loading, whether it's forces, whether it's gravity, moments, maybe some bearing loads, all those things can be analyzed with linear static analysis. That's pretty much the foundation of most analysis types. We can run modal. This is something we'll talk about today. Modal analysis allows us to find mode shapes and natural frequencies in our designs, and it's the foundation of all of our vibrational analyses. These two will be very similar to what you'll see with something like Inventor FEA, but you have a little bit more capability when it comes to setups and connectors, and I'll talk about that in a moment. You can also do things like nonlinear, so impact, drop tests, and permanent deformation. So if you want to look at how a structure responds to a standardized drop test, you want to see what would happen if you have some protective structures that might be struck by a large object. Those can be tested with impact analysis tool, as well as nonlinear transient analysis within Inventor Nastran. So there's a lot you can do there. You can look at individual time steps and look at your time-dependent response of your designs. Permanent deformation as well. So maybe you have a structure that is going to be worked to a point that it will go beyond its yield stress. So if you're looking at the nonlinear working range of any of your materials, you need nonlinear static analysis to do that. You also need nonlinear static analysis to look at large displacements, large deflections, things like that. And that's something that Inventor FEA and standard stress analysis tools cannot do. So as soon as you jump into Nastran, you get this whole new world of possibility in that you can really look at the full range of your design and the full working range of your materials. In addition, you get some advanced linear dynamics. This includes shock response spectrum. So if you have structures that, for instance, like multi-story buildings that will be subjected to seismic loads, that can be analyzed with shock spectrum response, as well as very sudden high energy loads, pyrotechnic, explosive loads. Those can be analyzed with shock response spectrum as well. Something we'll talk about today is random response. That's another advanced linear dynamic analysis, and that is neat because what we can do is we can look at random loading of our structure. So situations where we don't necessarily know the exact frequencies it will be subjected to, but we have some test data or some specification data we can use to estimate that. And just as a note, you also have things like buckling, fatigue, thermal analysis, and quite a few different options for connecting and simplifying your geometry as well. So most softwares, Inventor FEA, you'll just get your linear statics and modal analysis. If you need anything beyond that, that's where jumping up to Nastran is really going to benefit you. So just a side-by-side comparison for anyone that is coming from Inventor FEA or another software similar to that. You get quite a bit more with Nastran. You can really look at things like your element type based results. So you can look at shell elements and solid element results. You can check your quality of your mesh. This is an important one. You can get a really good idea for the quality of your elements and whether or not there's a lot of skew or poor aspect ratios in your elements. Basically, you can get a gut check on the quality of your element and how it will affect your analysis. You can do individual part-based mesh. That allows you, when you're working in an assembly, you can apply a mesh size to each part individually. With a tool like Inventor FEA, you have to use mesh controls to do that, and it can be very time intensive. So this can be a very advantageous tool when you're in a large assembly. You can do things like rigid and bolted connectors. Rigid connectors and bolted connectors allow you to simplify things like bolts, potentially substructures that you don't actually have modeled or you don't want to include in your analysis can be simplified with a rigid body connector. These are great tools to simplify your model size, but also improve the accuracy of your results by eliminating small elements that can lead to stress singularities. Custom coordinate systems, you can use any coordinate system you'd like. You can create new ones for specific constraints or specific materials and customize the direction of your X, Y, and Z axis. And then you get a couple things we'll talk about today. You get nonlinear analysis. So like I talked about before, nonlinear statics, nonlinear materials, transient analysis. And then you also get vibrational analysis, and that includes shock response. You can do vibrational fatigue as well as random response within Nastran InCAD. So you get a lot. Up until now, it's been labeled as Nastran InCAD. And then in 2020, now they've renamed it to just Inventor Nastran, just so you're aware of that as well. I'm going to talk about 3 different analysis types today. Number 1 is going to be our modal analysis. This will be the first type of analysis you'll want to run before you go into frequency or random response. So when we have a non-rigid system, that means a system that is constrained. So a rigid, basically rigid motion, which would be considered kinematics, would be something like an airplane traveling through the air. It's moving as a rigid body. Whereas when we're looking at dynamics and we're looking at natural frequencies here, the body itself is actually deforming. So we're constraining our part or our assembly, and we're looking at the body itself deforming under a vibrational load. So every single design will have natural frequencies and a corresponding mode shape or eigenvector. So we're going to be calculating those with our modal analysis. So the frequencies that we will get a mode shape. This is based on a sinusoidal shape that the object will take. Basically, the lower the frequency, usually the less complex the mode shape. The mode shape does not have any relevance to the displacement and stress. It's scaled to a max value of 1 and -1. So all we're getting is a representation of where the mass in our system is going to move. So the displacements and stresses are irrelevant with this type of analysis. The shape that we are getting is just a theoretical shape that shows us exactly where we can expect the mass of the system to shift under that specific natural frequency that we get. So those are our results that we will get from this. We'll get natural frequencies and mode shapes. And these frequencies allow us to determine what operating speeds and conditions might produce what's called a resonant response. So let's say we have a motor that is spinning and running at approximately, maybe it's putting out about 50 to 60 hertz based off of the RPM. If we have a structure that is supporting that, and the natural frequency of the structure is somewhere between 50 and 60 hertz, that could be a problem. And that's because you'll see what's called a resonant response. You'll see more of the mass moving around and vibrating and increasing with each cycle to where you can actually have the structure sort of shake itself apart or potentially displace enough to loosen bolts, reduce the strength of some of your connecting components, and potentially cause a significant amount of damage. And it has nothing to do with the static loads coming into the system. It has everything to do with the natural frequency and the resonance response being created. So we're creating an excess vibration or resonant response that will lead to significant damage. So by running modal analysis, we can determine our structure or our part, what frequencies might be an issue. And if those are close to our known operating frequencies, we can then do what's called a modal avoidance exercise. And what that means is all we're doing is we're changing the connections, the materials, the stiffness, and trying to adjust our natural frequency so that it is further away from our operating frequency, getting it into a safe range. So we can also control the mode shapes at specific frequencies. So for instance, if the mode shape at a specific frequency has a lot of mass moving in the Z direction, and that's going to be problematic for your displacement, you don't want it to vibrate in the Z direction, you can adjust your design so that it eliminates that mode shape and maybe shifts the mass in a different direction that won't be as problematic. So there's a lot we can do with the data we get from modal. However, we don't have any true displacements or stresses. That's something we would need frequency response for. So frequency response is taking it a step further. What we're doing with frequency response is we're looking at our structural response to enforced sinusoidal loads. These will typically be accelerations. So for instance, you can have things like rotating machinery, unbalanced tires, helicopter blades. All of these will produce a sinusoidal load function that looks like this. So you have that sinusoidal load input coming in. Based off the frequency, that sinusoidal load will look different. However, all of these types of situations can create that type of input. So what we want to do is determine, based off of that sinusoidal input, what amount of displacement and stress will we see in our system? And will it be significant enough to cause damage? Will we be going beyond a specified displacement range? Maybe we have some tight clearances. So using frequency response, we can go ahead and determine what our required damping is going to be. So get an idea for what level of damping will reduce the displacement to an acceptable amount. So you can play around with the damping and try out different damping values to determine what's going to be best. You can avoid damage, which is a really key one here. Looking at this allows you to determine how much stress will be caused by this level of vibration, and over the long term, if this were to be a constant vibration, what level of fatigue we might see. And very importantly as well, we can understand the magnitude of displacement. So how much deformation will we see? Will we see the component or the assembly displace a significant amount to where we're having clearance issues, or will it be a manageable amount of bending or deflection? So with frequency response, what we can do is we can take specific input frequencies. So we can go ahead and say, all right, we're going to test this from 10 hertz up through 500 hertz. Maybe we increment it every 5 hertz, and you can get what's called a frequency sweep. So you can check all the frequencies in a specific range and determine where your peak responses are. So basically, you'll get a plot that will look something like this, where you have a some vibration occurring, and then you'll see a peak response in the displacement. It'll vibrate a little longer, and you'll see another peak response. So these peak responses is where the displacement and the acceleration increase due to that frequency being close to a natural frequency. You'll get these peak responses that you can then determine what the displacements and stresses are. So let's say that we cannot quantify the loading. Maybe we don't know exactly what frequency the design will be subjected to. Maybe we can't really put our thumb on whether it's going to be subjected to 50 hertz or 200 hertz. And we know we have natural frequencies in that range that we can't really completely avoid. So we just want to make sure that we understand the effect of a frequency range on our design and the effect of multiple frequencies sort of combining into a single result. This is called random response. So basically what we're doing is we're combining different frequencies into a single result. And so we'll sort of get a statistically based loading that allows us to calculate what I would consider the worst case scenario. So some examples you might see here would be components mounting on a moving vehicle. So if you think of a truck driving down the road, let's say it's a bumpy dirt road, there's going to be a lot of factors there. You may not know exactly what level of vibration it's going to be subjected to, and it's probably not going to be constant. It's not like driving down the road, it's constantly going to be vibrated at 80 hertz. It could be 50 hertz, and then you hit a bumpy patch, and that could jump up to 200 hertz. You could have all these different frequencies combining at the same time. You could have a portion of the vehicle being subjected to one frequency and another part of the vehicle to a different frequency. So what your plot would look like, so if you were to take your acceleration and plot it over time with an accelerometer, you get a plot that looks like this, where you have a lot of white noise. And it's difficult to quantify, what level of acceleration we're going to be seeing, and it's not sinusoidal. The input does not look like this. It's not sinusoidal, it's more jagged and hard to characterize. And so when that happens, we need something like random response to give us an estimated worst case scenario. So moving vehicles, spacecraft. So when you have a launch vehicle, you can see external acoustic pressure look very similar to that, where you get that white noise acceleration due to acoustic pressure. Also, airplane wings in flight. If you've ever been on a window seat on a plane and maybe you're flying into Denver like I do regularly, you look out the window and sometimes you'll see some turbulence causing that airplane wing to be really moving quite a bit. You can see a significant amount of displacement. And that level of loading can be difficult to characterize. Again, it's not constant. It's going to be very random, and you might have a combination of multiple frequencies where it's still vibrating from a previous load when it's hit with another wind gust. So you get multiple frequencies being activated. So what we can do with random response is we can get our system response due to multiple frequency inputs based on probability. So when you get into random response, it can be a little bit tricky to understand sort of where they're pulling in what's called this PSD from. So this is called power spectral density. The curve will look something like this over here on the right. Basically, the power spectral density is going to be a measure of the amount of energy in our system at each frequency range. So over on the left here, if you were looking at a plot of acceleration versus time, you may not have a good idea for what the level of energy is going to be right off the bat. But if you take your signal and you square it, so you take the square of the signal, so everything is positive, and then you take the mean of that square, you can get an estimated value. They show this red line here. Even though you have multiple signals and the phases don't really line up, you can get a mean square value that estimates the amount of energy in that overall band. And from that, you can work to calculate what's called the power spectral density, or the PSD. So at the end of the day here, what we're really doing is we're looking at our mean squares here. And if you were to take the acceleration versus time and look at it as acceleration versus frequency, what you can do is you can take a band. So let's say we look from 20 to 30 hertz in this bracket. And in that frequency band, you may not see very many accelerations. You only may see it hit, let's say, it hits 1 G of acceleration, 5 or 6 times over that entire data range. The likelihood of seeing 1 G of loading is pretty low. However, if you were to look at a frequency from 10 to 20 hertz, the statistical probability of seeing, maybe a half G of loading might be significantly higher. So basically, we're building a histogram of our inputs and saying there's a high likelihood that we will see half a G of loading, and there's a very slim likelihood that we'll see 10 Gs of loading. So using that, you can build a power spectral density curve that estimates the amount of energy at each frequency band. So at 20 hertz, you can expect this level, 100 hertz, this level, 1,000 hertz, this level, and then 2,000 hertz, this level. So for instance, this chart they show here, the most energy exists between 10 and 1,000 hertz. So one very important thing with random response is it is a statistical process, which means the result that we get is only 1 sigma certainty. So we're only about 68% sure that we will not see any displacements or stresses that exceed that. So in order to be 99% certain that we won't see any stresses or displacements that exceed what we get, we need to multiply our results by 3, and that will assure a 99% certainty. And that is sort of the industry standard for this type of testing. So what would a PSD look like? So if you look at an example here, this is from mil-spec standard 810G. So there are typically standards based off the environment that you will be subjecting your design to, whether it's a spacecraft, upper stage, whether it is a vehicle. This one here is common carrier, highway truck vibration exposure. So if we were driving down the highway, this PSD has been formed from test data of trucks driving down the highway. They pulled accelerometer data and calculated this PSD. And it has 3 components: vertical, transverse, and longitudinal. So typically vertical will be the most damaging. That would be in the vertical direction with gravity. You also have transverse and longitudinal. So you can look at each of those. So you could subject your design to all 3 of those and see sort of which one causes the most damage. In this case, for this example, I'll be using vertical. So we'll be using the vertical PSD. So I'll be pulling from the spec and using 10 hertz and the corresponding G squared per hertz PSD value for this type of testing. So most of the time, you will be pulling data from a mil-spec, something like this for highway trucks. You could also find a mil-spec for things like launch vehicles and what they need to be subjected to. You can then determine if using random response, your design is still acceptable under this type of loading condition. So I wanted to kind of show you a example of where you might see this type of analysis run. So looking at just a skid here, this is a skid that will be used to mount a pump. So I'm going to have this pump here. And I just built a design that's representative of something that might look like that. So I just built a simplified version of this where I have some cross members and then a pump stand that I'll be mounting that pump onto in the very center. So I'll walk through sort of what I set up for this analysis. But this is something that Number one, because I will be getting some vibration from that pump, I'll likely want to run modal analysis and make sure that I'm not near that natural frequency. I'll probably want to run frequency response because due to the vibration of that pump or the motor, depending on what I'm mounting here, I'll likely see some sinusoidal excitation. And then if this was being mounted, let's say it was actually being mounted onto a truck. A lot of times you'll have skids with pumps and things like that mounted on the trucks. That's where I might be subjected to road input loads, and I might need to run a random response analysis. So I'm going to kind of showing the process of setting up all three of those for something like this. So jumping over to Inventor, this is the original design. It was just basically some, this is all built with frame generator and then a simple sheet metal component in the middle. Basically we have some standard frame components along the sides, some box tube members that will be cross members and they will be welded at the interface there. And then this mounting frame for the pump or the motor is going to be bolted with 4 bolts on each side. And then the frame will be, basically the pump or the motor is going to be coming into these 4 slots along the top. So rather than designing and including the entire pump system and the motor, in this case, I'm going to be simplifying it to a concentrated mass. So it'll be a centered mass that will be tied into the 4 slots with the rigid body connectors. So that will simplify my analysis. So first what I did was I simplified this into surfaces. So I simplified it into mid-surfaces. This allows me to use 2-dimensional shell elements, which will be much higher quality because of how thin these are. You'd have to get 2 or 3 elements through the thickness of these solid elements, and that's going to be very difficult considering how thin they are. So using shell elements is going to be very advantageous here. So looking at our setup, this was set up to be constrained, where you see those black constraints along each side where this is going to be welded or mounted into a larger supporting structure. I am also applying bolted connectors at the interface of the pump stand and the outer channel there. So with these connectors, you can apply a connector to each side. So this basically allows you to select the bolt head side and the bolt nut side, specify the bolt diameter and the bolt material, and it'll then treat it as essentially a line element running through the center of that hole with a rigid body connector tying into each edge. So this, even though I don't get the stresses on the actual bolt surface, this gives me a very accurate representation of the bolt strength and how it would transfer the load from one surface to the next. You'll also see where I have the welds, I don't have any contacts applied because I use what's called continuous meshing. So anywhere you have the edge of a shell element going into the face or the edge of another shell element, if you go to mesh and you check the box for what's called continuous meshing, and this is something that Inventor FEA cannot do as well, you will get the nodes lined up. So it lines up the nodes on the face here with the nodes on the edge of the box tube. So that what you get is essentially a representation of a weld bead being laid along this line. So the stresses will be transferred from one element into the next very evenly. And this reduces the number of contacts you need, and it can really speed up the analysis process. So if you know you're going to be welding that together, it's a safe assumption to use continuous meshing between the edge of that box tube and the face of our frame component there. So there'll be welds here, and there'll be bolts for the frame. And then the pump stand itself has been simplified into a concentrated mass. This represents, I think it's something like 100 pounds is what I made the mass, and it is tied in with rigid body connectors from the center point of the mass to the slot edges where it'll be mounted in to the larger structure. So this is just a kind of a simplified example of how you might take a complex structure like this and simplify it into shell elements and use bolted connectors and rigid body connectors to eliminate the number of contacts that are required. The only place I have contact is between the face of the pump stand and the face of the structural member, where I might see this deflect enough to push into that face. I have a separation contact applied there so that we get a transfer of load from one face to the other. All right, so looking at our first step, we're going to do modal analysis. So when you're looking at your analysis types, you have linear static will be the default. You have normal modes below that. You'll see down in the second section here, you have modal frequency response and direct frequency response and random response as well. Those are sort of the options we'll go through. So if I set normal modes on here, you will get the same setup properties as a linear static analysis, except you'll also have an option called Modal Setup in your analysis tree. So if I right-click on Modal Setup and select Edit, I can then modify the number of modes that I calculate. So I could say, you know, for my first analysis, maybe I want to calculate 20 modes. I recommend starting with between 20 and 30 modes. And you will need to determine exactly how many to calculate when you get into frequency response. I'll show you how we can do that. But with normal modes analysis, 20 to 30 is a good starting point, and you can always increase it from there as we go forward. You also can use a high and a low frequency cutoff. So you could say, I am actually only interested in modes between 10, let's say 10 and 1000 hertz. You could do that as well. And that will just bracket the analysis so it does not pull modes that are lower than 10 hertz and higher than 1000 hertz. You can do that as well. So once you have your modal setup, then you just need to make sure you have constraints applied. So I have these edges of my frame constrained, and then you can choose whether or not you want to apply gravity. So you can apply gravity, you can also apply external loads if you believe that those will create a significant amount of stiffness. And in that case, I would also recommend considering running pre-stress normal modes in addition and comparing the results. Pre-stress normal modes will apply the load first and then run normal modes analysis. So this can stiffen your model under that load before running your normal modes analysis. But most of the time, the results will be fairly similar, but I recommend running both and comparing the actual result that you get. As a starting point, I'm just going to run this with no loads applied, so I'm not going to apply any load. I'm just going to be looking at the structure itself as though it is just sitting and there are no external loads being applied to it. So it's just being mounted into a larger structure here. So once we run modal analysis, the results that we get will basically just give us our natural frequency, and at each natural frequency, or each mode, we have that natural frequency set. So I calculated 20 modes, so I have 1 through 20 in my result set, ranging from 73 hertz all the way up to 710 hertz. So my first natural frequency is going to be 73 hertz. And if I click on it, I can display the mode shape. Now again, this displacement and stress is not relevant. This is just showing the shape that it would take under that vibration, and it gives us an approximation of where the mass would shift to. So looking at this, we have quite a bit of mass moving in the Z direction, positive and negative. So it's sort of twisting. So we're also getting some rotation about the y-axis in this scenario. If I want a better viewpoint, I can turn off my concentrated mass as well as my connectors so it's a little bit easier to see. Maybe I'll also turn off my mesh controls. So now you can really see that shape. If I go to mode 2, it's a frequency of 102 hertz. This is showing displacement now, and you can see that it is mostly the mass shifting along the y-axis here. So most of the mass is moving in this direction. So you can see that shift occurring. So this gives us an idea for, number one, what that natural frequency is, and if that natural frequency, if that mode shape is going to be in a specific direction. So we can see that mode 1, there's a bit of twisting. Mode 2, there's motion along the y-axis. Looking at mode 3, we have quite a bit of mass moving along the z-axis. So this would likely be a very damaging mode if we have an operating frequency near this, because It's a relatively low frequency, only 105 hertz, and we have quite a bit of mass moving in the Z direction, which is going to really strain this pump stand sheet metal, probably more than shifting along the Y-axis or the X-axis. So this will likely be a more damaging mode. So we don't really know the amount of damage or displacement, but we can get an idea for what natural frequencies will be an issue. So if we have an operating frequency near 73 or 100 hertz, we'll likely want to adjust the materials to push the stiffness high enough that the natural frequency will be higher than that. So that's normal modes. Again, set your number of modes between 20 and 30, run your analysis, and then make sure that these natural frequencies that you get, none of them are near your operating frequency. So it's a good quick check that you can use to determine where you're at. So let's say that I actually do need to determine the effect of some of those frequencies. Maybe I can't avoid them in my design. I just want to make sure that if that frequency is activated, I won't be seeing enough displacement or stress to cause damage. I can use frequency response. So there's two types, modal and direct. Direct frequency response, I recommend if you have a fairly simple problem, you don't have a lot of connections and contacts, and also if you are looking at like one or two specific frequencies, that's where direct frequency excels. But if you have a larger problem with more connections, connectors, more elements, and you also have a large number of frequencies that you need to check. So in this case, I'm going to check a pretty large range of frequencies. So I'm going to use modal frequency response because it's a little bit more efficient. What it's going to do is it's going to take the number of degrees of freedom in my system and simplify it to a modal degrees of freedom. What that comes down to is it's going to simplify the problem and solve quicker. It's also going to be giving me results that will be just a little bit more optimized for larger designs. So I'm going to be using modal frequency response here. The one thing with modal frequency response is I do need to set modal setup once again. But if you copy this over from your modal analysis, so if you right-click on your analysis and you duplicate, you can then bring it in with the same modal setup parameters as your modal analysis. Now, to determine how many modes we need, I recommend using the output file that you get from your modal analysis. So we'll go and grab this folder. So in the location on your computer where you run your analysis, so wherever this file is stored, Nastran automatically creates a folder. It'll be called the pump frame FEA here for me because that's the name of my assembly. And in that folder, if you dig down into the FEA folder, you'll see files based off of the analyses you run. So I've run 3 different analyses in here. So there's different groups of files. You'll basically have these 6 files right here for every single analysis that you run. The FNO file holds all of the results for your design. So it holds all of the contours. So when I load in my analysis into Inventor Nastran, that holds all of the contour plots, so my stress and displacement contours. It shows up for me as a mold design file, but if you right-click on it and go to Properties, the .out extension, that file holds all of your results in a tabulated format. So you basically have a bunch of tables of your results. From that, I can determine what's called the modal effective mass. So you can open this with Notepad, or I prefer to use Notepad++. And in here, you can search for what's called the modal effective mass summary. So I'm going to go to Control F, and I will search for P space E space R space C. So you have to add in spaces because the way that the text is laid out in this file, there's a space between each letter. So I'll go to Find Next, and it finds my % modal effective mass table. And what this is you have along the top T1 through T3, R1 through R3. This represents our 6 degrees of freedom. So basically T1 is X, T2 is Y, and T3 is Z. Same with R1, R2, and R3. So that's R1 is rotation about the X. R2 is rotation about the Y. These are our 6 degrees of freedom. Along the side, you'll see mode number 1 through 20. And then for each mode, it shows the amount of modal effective mass, so the amount of mass that will move or is sensitive to that mode number. So you can see mode 1, we have quite a bit of motion or mass participation along the X translational. Also quite a bit of rotation about the Y. So if you remember from looking at the modal analysis results, we had quite a bit of rotation along the Y-axis in mode 1. Remember mode 3, we had quite a bit of Z mass. That's because 41% of our mass is going to be participating along the Z translational direction for that mode. So basically what we want to do with this is make sure that when you sum all of these up, when you go to this percent modal mass table, we want to see that the sum of the mass participation in each direction is 80% after we've calculated all of the modes. What that does is it makes sure that we don't miss anything that's critical. So let's say we only calculated 10 modes. You'll see down here, mode 13, it has 14% of the mass rotating about the Y-axis. And that could be enough to do some damage. So we want to make sure that we are not missing any modes that have a significant mass participation. So in order to do that, we can just make sure that we have at least 80% every direction. Here you can see that in the X translational, Y rotational, and Z rotational, I don't have 80% yet. So what I need to do is I would need to run more mode calculations. In this case, probably something like 40 to 50 modes will give me 80% in every direction, but you don't know until you actually run it. So you will want to make sure you have that before you run frequency response or random response. You need to know that you're getting 80% in every direction so that you're not missing any critical modes. So again, this is in that .out file, and you can open it with Notepad or Notepad++, and then this percent modal mass table gives you those percentage values. So for frequency response, I would want to bump this up to, something like 40 to 50 modes, just to make sure that I'm capturing 80% every direction. So that's the first step, is determining how many modes to calculate. Step number 2, set your damping. So damping with modal frequency response, I'm going to use modal damping. For a welded structure with a few bolts like this, a good damping value to start with is going to be something around 5% structural. So critical damping is half of structural. So if I do percent critical, I could do 2.5%, and that would represent 5% structural damping. And damping is a more complex subject. There's kind of a lot of different methods you can use. Basically, with simple metal components that don't have a lot of complex connections, there's a lot of welds in this structure, it's mostly continuous. You could expect damping to be somewhere between 2 and 6% structural, somewhere in that range. Sometimes you might need more damping than that to stabilize the solution. And in order to really determine the amount of damping that is occurring in your system, you'd have to get some accelerometer data and filter that and determine sort of what acceleration peak responses you're getting. And then you'd have to run a study in Nastran NCAD and try to get the damping to produce similar results. And then you're at sort of an approximate range. For now, I'm going to start with 5% structural. That will be enough to not overdamp the system, but it will stabilize. And this is representing the amount of energy lost in the system. So we just need to make sure that we are approximating the energy loss appropriately, and we aren't underdamping or overdamping our system. The last part of the setup will be your dynamic setup. This is where you can specify your low and your high frequencies. So in this case, I'm going to use cluster between modes and spread around modes. What that allows me to do is with cluster between modes, I can take my peak responses. So let's say I have a natural frequency here and one here. What I can do is I can input the natural frequencies, and then I can add an additional cluster between each of those. So I can then add 5 more data points in between the first natural frequency and the second natural frequency. So I'm doing a frequency sweep. I'm getting all the frequencies between each natural frequency. I'm just evenly spreading 5 data points. So that's sort of just a shotgun method to kind of get a bunch of points between each mode. And if you combine it with spread around modes, what spread around mode does is it takes a number of points, so I'm going to use 5 points, and it spreads them within a percentage spread around each natural frequency. So if I have a peak response, it takes 2%, so 1% on each side of that natural frequency, and it applies 5 data points evenly around that natural frequency. So the effect of combining these two is I get some evenly spaced frequencies in between each natural frequency, and I also get a cluster of tightly spaced frequencies that are input right around each natural frequency. So this allows me to, number one, assure that I'm testing at each natural frequency, and number two, I'm getting a nice cluster around the frequencies where I can make sure that even if the natural frequency isn't showing a large amount of displacement, maybe a frequency nearby is also showing quite a bit of displacement, so I can make sure I'm capturing all of that information. So that's why I recommend combining cluster between modes with spread around modes. So that is my method that I'll be using here. The more data points, the better. I started with 5, but if you want a little bit more insight into your data, you might go up to 10 to 15 points. And that will just create a larger data set. But again, you have more insight into what's actually happening. For my loading, I applied a gravity load to the entire system. So basically every node will be subjected to gravity in the negative z direction. So for my load here, we have gravity. This is in the negative z. Now, if you want to make sure that gravity is basically applied constantly from 0 hertz all the way through, I'm testing from 0 to 500 hertz. Basically, if you want to make sure that gravity is applied evenly throughout, you can also use a load scale table. So you can apply a load factor. And if you say from 0 to 500, the load scale factor is 1 and 1, you basically just get a plot showing that the gravity will be input at a maximum of 386.4 inches per second squared at 0 hertz all the way through 500 hertz. So I'm getting an even load regardless of frequency or mode shape. So I'm applying gravity in the negative z direction. You can also apply your loads as forces. So any force that you apply in a frequency response situation, so if I apply like a 10-pound force load, it will be applied sinusoidally. So it'll be applied with a sinusoidal input. If you apply gravity, it'll act the same way. You can also apply your acceleration due to gravity as an enforced motion. And you can apply that to constraint locations where vibration's coming into the system. That will typically solve a little bit quicker, but gravity is a good place to start. And you can always compare those results to see if it's a significant difference. So I'm going to apply gravity. I will be applying 20 modes. I'd probably need about 40 modes to really get the full modal mass participation. So I'd come back and run this with 40 as well. Damping, we're using about 5% structural, and I'm testing from basically 0 to 500 hertz with our frequencies clustered around each mode. So looking at the results we get, basically I'll end up with quite a few frequencies. I think somewhere around like 130, something like that. Let me open this up. Basically, I started at 10 hertz and I went all the way up to basically step 135, which is 691 hertz. So pretty large range. What I can do is I can then look at what the response is at each natural frequency, or I can use a plot to get an idea for where my peak responses are. I recommend using plots to start. So under XY plot, you'll see max displacement versus frequency. This will give me a really good idea for where my peak response is going to be. So I'll double click on that, and it shows I have basically my frequency along the bottom, and then this is my displacement magnitude along the y-axis there. And I can see right at around 100 hertz, I have a spike in displacement where one of the elements in my system is going to suddenly go from very little displacement up to almost 25 thousandths of an inch. So a good amount of deflection under this level of vibration. And then right around 300 hertz, I see another peak response in displacement. So this gives me a really good summary of where my peak responses are. If you change your type to scatter, you can then see the data points. And you can see what I've done is I have 5 data points between each peak response, each natural frequency. Then you can see these clusters. I'll try to label them all. All these dark clusters show that I have a bunch of data points. And that's where I have that cluster around nodes. So I have a bunch of extra frequency inputs around my natural frequencies. So I had one, if you remember, near 70 hertz right here. I had another near 100. There's another one out near 200. So this shows you that that input was done with cluster. I can also look at the linear acceleration versus frequency. And I can see there's also an increase, quite a bit of increase in acceleration right around 300 hertz and another out around 550 hertz. And of course, the acceleration that I expect right around 100 hertz. So that appears to be one of the more damaging frequency inputs. So let's go ahead and see what the actual results look like. So I'll go ahead and go to 100 hertz. And it looks like I'm getting about 27,000 PSI for my shelf on MEC stress here. So this material has about a yield strength of about 40,000 PSI, so I'm below yield, but certainly an area of concern. And it's kind of where I would expect, right at the edge of that slot where I have kind of a sharp corner. But also that is where my mass of my pump is being connected into my system. So that's where I would expect there to be quite a bit of bending and deformation due to vibration, because that pump is going to start to shift around and strain the edges of these slots. So my results look about as I would expect, and using that displacement plot, I can determine kind of where I would expect to see the most damage, and I can see right at about 100 hertz, I'll see about 27,000. If I go up to like 101 hertz, I can see if that's any higher. So I can check right around the same area. Looks like that is about 29,000. So clearly between 100 and probably 103 here is where I'm seeing the most damage. We'll check 103, and that drops to 22,000. So it looks like at 101 or 102 hertz, one of those, because I had 2 natural frequencies right in that range, one of those is going to be the most damaging. So I can kind of filter through that and make sure. So it looks like 101 hertz is going to be the most damaging. So in summary, our frequency response, we can input a range of frequencies and determine which one will cause displacement and stress and what the magnitude of that displacement and stress is going to be. I can then go back and redesign or change the stiffness of my design to improve the response at that frequency, or try to shift the natural frequency away from that. Now, the last type of analysis here is our random response. This would be done if, you know, maybe I say, you know what, the way that I mount this pump with the RPMs that I'm seeing, that level of frequency is not a concern to me, should be okay. But I'm going to be mounting this onto a truck, and in its operating conditions, we might see random input. So if that's the case, I'll also run random vibration. And again, I could use data from a mil spec like this, or you can get some accelerometer data and create your own PSD curve, but it'll probably look something like this. So what I'm going to do is I'm going to take this PSD data. So we've got 10 to 500 hertz, and we have our PSD values here. So I'm going to enter in those three values into Nastran InCAD, and that is going to take my frequency response and scale it. So I'll be getting a what's called a RMS output. So I'll get a root mean square peak response. So we're going to be getting the statistically based summation of all of those inputs and getting a worst case scenario displacement and stress value. So when you switch over to random vibration, so it shows up as random response, you'll notice everything looks the same. You have your modal setup. Again, use the same parameters as you use for your frequency response. You have your damping. Again, I would stick to the same damping as your frequency response. And when you go to dynamics, you'll also have the same input cluster and spread around mode options. You can also input in discrete specific frequencies or frequency range. But at the very bottom corner, you will see random analysis options, and this is where I can go through and apply that PSD. So if I click on this table, I went through, grabbed that data, and I applied 10 hertz with my specific PSD values, 40 hertz, and 500 hertz. So this will represent the amount of energy in the system at each of those frequencies. And when you apply this, make sure that you log the X and the Y. The reason is if you look at this data, your data should match the way that data is coming in, and it is log scale. You'll see that it was log on the X and log on the Y. So make sure that your data is input the same way. So this will be log scale. So if I click on show XY plot, this should look just like the input curve from my data. So I'm looking at vertical. So that should look exactly the same, and it does. I'm looking at 10 to 500 hertz. Make sure you log, and also make sure that your type is acceleration versus frequency. That's the most commonly used spec data for something like this. So we'll go ahead and use 10 hertz through 500 with those corresponding PSD values. And when you run your analysis, and I have the setup, everything else is exactly the same as my frequency response. Gravity is still being applied. When you look at your results, you're going to get a list of frequencies. Those are our frequency inputs that we use for basically our modal frequency response, which is run on the front end. You will see PSD scaled frequencies. So we have steps here. This is our frequencies just like we had for modal frequency response. The second grouping is a PSD scaled frequency. So you'll see PSD frequency. So it's taking the frequency response and scaling it based off of our energy curve that we input in. The most important thing that you will use is going to be your RMS output. So this is taking the square of the area under that resulting curve and giving us again, a statistically based summation of those inputs. So we're getting a worst case scenario stress and displacement. So if I plot my stress, so I plot that RMS output, that root mean square output, I get a plot that looks very much like my frequency response analysis. However, this is considering all of those different input frequencies and their effect on our results. So I can see it's showing about 10,500 PSI near that edge. And this is saying that there is a 68% chance that you won't see any stresses higher than 10,558 PSI. However, if I want to make sure that I'm 99% certain, I need to take that value and multiply by 3. So there is a 99% certainty that I will not see stresses that are higher than 31,674 PSI. And the yield strength of my material is 40,000, so I'd still have about a 25% margin, which should be enough here that I'm not really too concerned about this causing damage. You can also check displacement because you may be certain here that your stress isn't going to be an issue. But let's say that this is mounted such that there's a very low clearance between the bracket or the actual pump and the enclosure that it's built into. Or maybe there's other pipes or things running nearby. You may have a tight displacement window. So that's where you'll want to check displacement as well. I have about 0.007 inches of displacement. So I take that and multiply by 3. About 21 thousandths of an inch. I can be 99% certain that it will not deflect more than 21 thousandths of an inch. And that is in the vertical direction. So I could also then take our PSD values here in the transverse direction, for instance. I could input in the transverse PSD curve and check that with the load in the transverse direction. So you can check all 3 directions from that mil-spec. But in this case, based on my design, I'm assuming that vertical is going to be the most damaging. But typically, you'll want to input in multiple data curves. You might even consider different operating conditions. So this is just a truck driving on a highway. You might go and find other mil-spec data for instance, like a smaller vehicle or a car driving on a bumpier road or gravel road, potentially, just to compare those results and see how sensitive your design is to different PSD curves in different directions. But this does give me a good idea for worst case scenario. If this is being mounted under a truck driving down the highway, I shouldn't see stresses or displacements larger than this. Even though I don't know exactly what frequencies it will be input, I know that under that operating condition, I shouldn't see energy that causes more damage than this in that situation. So that's sort of a rundown of what we have available to us in Nastran and CAD. Again, modal analysis, we can get our natural frequencies and our mode shapes and determine which direction our mass is moving. Frequency response, we can input those frequencies and determine the stresses and displacements that result from that. And random response, when we can't quite characterize our load and maybe we have multiple vibrations coming into the system due to something more complex, that's where we can use random response to estimate using probability the amount of energy in our system and what the worst case scenario would be. So I'll pretty much wrap things up for the presentation and demo. I hope that was informative to you guys. Obviously, there's a lot of information there, and I wasn't able to, really dive deep into the details. So if you think this is something that you'd like to do moving forward and you'd like more training, we do provide training for any type of analysis within Nastran. We also provide consulting, so if you'd like to look at a specific project or design you're working on and learn how to set that up, we can also guide you in that process as you begin to use the software with more complex situations. So feel free to reach out. And now, if you have any questions, I know Cassie's been fielding those throughout this presentation. So try to get your questions answered, and feel free to reach out after today, in the next week or two if you have further questions on any of these.